Till now, over the last 10 to 15 classes, we have been looking at the problems associated with supervised learning, wherein our objective was to predict something, right? So, prediction was the major objective. We always had one target variable there and then a set of feature variables. We were trying to build a kind of relationship between the target variable and a set of feature variables. And that is what we called as supervised learning problem. Within this, the two major categories is a categorical variable or the target variable is like a numerical variable. If the target variable is a categorical variable, we called those kind of problems as classification problems. And if the target variable is a numerical variable, we call those kind of problems as regression problems. But otherwise, the problems are one and the same. And we have used so many models to solve these classification problems, and the same can be applied to regression problems, except for small changes. Probably there is a logistic regression, which is primarily meant for a classification problem. There is a basic perceptron, which is primarily meant for a classification problem. And there is naive Bayes, which is primarily meant for a classification problem. Similarly, here we have seen the ordinary least squares regression, which is a linear regression, which is a pure regression problem. And we had looked at lasso and ridge regressions, which are also purely for regression oriented problems. Whereas all other models that we have looked at, support vector machines, the decision trees, the random forests, the gradient boosting, right, and also the KNN. We have looked at artificial neural networks, which is the multi-layered perceptron. We have looked at so many such kind of models. All these models are very well applicable to both classification problems as well as regression problems. It does not matter. So these are the various algorithms that we have looked at, and we have implemented the execution of these algorithms on our data sets. So that is where our supervised learning problems, we have decently covered some elements of the supervised learning problem. Now we are moving to our next problem, which is the unsupervised learning. In this unsupervised learning, there is nothing called prediction. We don't predict anything here, right? So one thing that we might do is we might group the observations. We might group the observations. So that grouping of the observations is typically called as clustering. So we might create groups in the data. Instead of someone giving us the groups in the data, we look at the patterns of the observations, and based on that, we group the observation. So probably you can think of segmenting the customers, right? Grouping the products based on various features, right? These are all the various examples that you can think of for clustering kind of problem. Okay, we will so clustering the problem. So we would look at segmenting the customers. Or sometimes you talk about various products, you want to group the products based on the similarity of the features, etc. So this is what we are going to look at now. How do I really create the groups of observation? So most of the times the grouping is based on similarity or the distances between the observation. The grouping is done based on the similarity or the distances between the observation. So we earlier also we said we in a prediction exercise also we had something called KNN problem, which was a distances based kind of a classification algorithm. So here also we are using the distances based only, but of course here there is no prediction. Here it is simply grouping of the observation. We'll look at that. But distances are going to play an important role here as well. So initially we will talk about the distances, what are the different kinds of distances. And here I will be talking about three major algorithms for doing the grouping or clustering of the data. One is called as the k-means algorithm. The other one is called the hierarchical clustering. And the third one is called density-based clustering, DB scan. Right? So we will talk about all these three kinds of algorithms, how to group the data using one or more of these algorithms. And what is the primary purpose associated with doing this kind of a grouping. So many a time you may not know, see you have different features, but you may want to know which customers are more or less similar in their behavior. You may want to know which products are more or less similar, very close to each other in their behavior, in their performance. Which stocks are more or less similar to each other in their performance over the last 1 year or 2 years. You can think of all these kinds of examples. So to address all these kinds of examples, we can very well get into the process of distances and then getting into each of these algorithms. So just like earlier, we will discuss about the algorithms and then we will implement these algorithms in our Python code. All right. So any questions on the conceptual aspect, just let me know. Then we'll just move on to our code part. All right. If there are no questions, then I'm going to move forward. So initially, we will talk about the different kinds of distances. We have already discussed them when we talked about the KNN, right? There also we use the distances, but here I have just slightly documented some of them just for a quick revision and reference. So distance metrics used in both supervised and unsupervised learning. In supervised learning, KNN is the most important distance-based learning algorithm. Whereas in unsupervised learning, different clustering algorithms. both k-means clustering as well as the hierarchical clustering. Both of them use the concept of distances. Probably the density based can also uses it, but not as rigorous as being used by the other two algorithms. But overall distances is something that plays a very important role when it comes to clustering. So in unsupervised learning, the role of distances is very, very higher compared to supervised learning. Finally, the objective of calculating the distances is to see how close are the observations to each other. How far away or how close are the observations to each other. So you could clearly see here that there are different distance learning mechanisms. Obviously, when we talked about KNN, we talked about the first three. The Euclidean distance, the Manhattan distance, and the father of these two, which is the Minkowski distance. Because in Minkowski distance, if I set the power to be equal to 1, then it becomes a Manhattan distance. And if I set the value to be equal to 2, then it becomes a Euclidean distance. The fourth distance is the Hamming distance, especially when we are working with textual data. The distance between the two words in a textual data is typically measured by Hamming distance. We'll go there. So as we have already talked about, the machine learning algorithms that use the distance metrics are the clustering algorithms. All clustering algorithms in some form or the other, they use the distance metrics. And similarly in classification, the KNN algorithm definitely works on the distance metric. Now, if I look at each of these distances, Euclidean distance talks about the shortest distance between the 2 points. So we have already talked about them earlier. So the Euclidean distance always talks about, if at all I have 2 points, x1, x2, x3 are the values for the first and probably y1, y2, y3 are the second observation. So the first observation is x, second observation is y, third observation is z with values z1, z2, z3. Then the distance between x and y is nothing but square root of x1 minus y1 whole squared plus x2 minus y2 whole squared plus x3 minus y3 whole squared. So this is how the distance is found, and this is what is typically called as the shortest distance between the 2 points. Right? Most machine learning algorithms, including k-means, use this metric to measure the similarity between the observations. So though there are various distance mechanisms that are available, the most commonly used distance mechanism is still the Euclidean distance. So if you really look at it, if I have my first observation with values 1, 2, 3, the second observation with values 4, 5, 6, then what we typically see is we can find out the Euclidean distance between these two, which is square root of 4 minus 1, which is 3 squared, which is 4 square root of 9 plus 9 plus 9. So square root of 27, which comes out to 5.19. So that is how I get the Euclidean distance between the 2 points. Okay. Similarly, when you talk about the Manhattan distance is the sum of absolute difference between the points. So basically here the Manhattan distance between x and y will become modulus of x1 minus y1 plus modulus of x2 minus y2 plus modulus of x3 minus y3. So this is what will typically become the distance, Manhattan distance between the points. So we could see if I have 2 points, 1, 1 and 5, 4. If I go with the Euclidean distance, then it would be square root of 5 minus 1 whole squared, which is 4 squared 16, plus 4 minus 1 whole squared, which is 9, which becomes square root of 25, which is equal to 5. This is the Euclidean distance, which happens to be the shortest distance between the 2 points. Whereas the Manhattan distance here will become modulus of 1 minus 5 plus modulus of 1 minus 4, which is what is going to become 4 plus 3. That is what is going to be 7. So the Manhattan distance between the 2 points is going to be 7. So you can very well compute those distances, right? We can very well compute those distances, right? Probably you can see the kind of a coding that we are using. There is a SciPy from the SciPy library. We are using a module called a function called distance. Now, in this distance, we have different kinds of distances. So probably if you look at this distance computation, we have different kinds of distances out here. So if I say distance, probably I'll just type it, right? When I say distance dot, here you see there are all these. So I can take Euclidean, I can take Hamming distance, I can take Jacquard distance. There are so many. I can take Janssen distance, I can say Kulsinki distance, I can say Mahalanobis distance, Minkowski distance. There are different kinds of distances that we are seeing. Right, the city block typically is associated with the Manhattan distance, but these are the various kinds. Of course, different people have come out with different definition of the distance between 2 points. But the most famous ones are the ones that we have typically looked at. Okay, so the Minkowski distance, as we have said, it's a generalized form. Right, probably what it can take is x1 minus x2 to the power n. It goes like this: r to the power lambda plus y1 minus y2 to the power lambda plus z1 minus z2, or probably, sorry, here if I go with the same example, x1 minus y1 to the power lambda, x2 minus y2 to the power lambda, x3 minus y3 to the power lambda modulus. All of them added and they are raised to the power 1 by lambda. So this is what will become the Minkowski's generalization. But what you could see is, if lambda is equal to 1, it becomes a Manhattan distance. And if lambda equal to 2, it becomes a Euclidean distance. You could see that those calculations will typically match. right? Then it calculates the Manhattan distance, and if lie, you can very well specify, right? In the SciPy when you are showing, probably you could see here, I can either use the Euclidean distance, I can use city block function to get my Manhattan distance. I can use Minkowski and I can give the parameter as p equal to 1. By giving that parameter p equal to 1, I can very well get the Minkowski distance. I can give p equal to 2 and I can get, I can get p equal to 2 and I can, okay, by p equal to 2, I will get Euclidean distance. And by setting p equal to 1, I'll get my Manhattan distance. And otherwise, I can set any other p also because that's a generalization that I can set. And by setting p equal to 3, I get some other distance. So basically, you could see the if I'm talking about 2 points, Euclidean distance is 5. We have already looked at it. Manhattan distance is 7. We have already looked at it. But using the Minkowski distance also, we got that same 7 and 5. But if I put p equal to 3 and all, I get even more a smaller value. But generally, we don't use them in the practical applications. All right. So that is one dimension. Any thumb rule which distance measure to use where? Okay. See, there is, let's look at a bigger story, right? The big story is whatever we are able to do as a classification, right? Let's say we have 100 customers. We have classified them into, let's say we want to classify them into 4 groups, right? And there should be some significant difference across the groups, right? Between the group should be very significantly different, and within the group they should be very close. So whichever mechanism is able to bring that kind of a deviation for us, by using whatever distance, if I am able to create clusters which are well differentiated from each other, and the elements within the cluster are very, very cohesive. So that is what is the measure. So which means I can use all the distance measures, just like the way we talked about with respect to the prediction algorithms. Here also I say the same story. Just like the way we have used various algorithms and we have used some metrics to evaluate which algorithm performed better compared to the other algorithms. Here also, we can do the same thing. Here also, we can try different distance measures and then see which measure has actually been able to bring a clear-cut distinction or bring a clear-cut grouping among the various observations, where the intergroup distances are very large and intragroup distances are very small. Does that make sense for us? Okay. So because they're not only these few distances, probably we have lot many other distances as you have seen. You just type distance dot, you will get so many other algorithms as such. All right. Then we are talking about the Hamming distance. So Hamming distance is not applicable in case of numerical data. That's the reason we did not discuss it out earlier. Probably in some kind of natural language processing, we'll try to see utilization of it. Okay, for Latlon data set. Even in a Latlon data set, see, normally speaking, the Euclidean distance will give you a straight line distance between the 2 points. So in a spatial node, if you have to calculate the distance, see what is happening between the Euclidean and Manhattan, if you understand. The Euclidean is giving something like a hypotenuse of a right angle triangle between the 2 points. Whereas the Manhattan is giving the x-axis and the y-axis summation. So normally speaking, from a logical standpoint, it is always like the Euclidean distance has a practical, what you call, you can define it practically. But so that is like a air distance. But if you say no, air distance is something that I am not interested in, I am interested in a land distance, then you are primarily talking about the x-axis and y-axis separately, right? So if there is no kind of a direct measure between the two, so in that case, even it is a Manhattan distance as well. But definitely the Euclidean distance will have a higher priority than the Manhattan distance. Okay. But the more better way of answering it is depending on my application. If I have to group, see, normally if I have to group a few places based on their proximity, obviously I am more interested in a Euclidean distance itself, because I mean I'm talking of these places are very close off to each other, right? Rather than trying to measure them on the x-axis and the y-axis separately. The more closer they are can come from the, but if you say no, that there are no direct paths and they have to go only horizontal and vertical kind of a path, then obviously Manhattan distance would be the more appropriate kind of one. Okay, someone advised me to use the cosine distribution is fine. No, but this is Haversine, right? I mean, I'm not fully sure of it. Let's quickly look at it. Great circle distance, okay, in a sphere. Greatest circle distance between the 2 points. Okay. So if I have, okay, I think it looks fine. It's a special case of a more general formula in spherical trigonometry, the law of Haversine's, that relates the size and sides and the angles of the spherical triangles. So looks like, okay, if there are 2 points A and B like this, okay, so this is how it looks like it is coming. Delta latitude, you are taking the difference of the two latitudes, delta longitudes, and R is the radius of the earth. Okay, this is more and more specific to Latlon, right? This is not a generic spatial distance. So it looks like D is the okay radius of the Earth. D is the distance between the 2 points. So this is like a ratio of the distance. Law of I think so I need to really look at. I think there is a formula and all, but yeah, we have to decode this a little bit. Right, we are starting off with the difference of longitudes, starting off with the difference of latitudes and longitudes. D is the distance computed between the 2 points. So here A is coming out as sine square delta latitude difference by 2 plus cos lat 1 times cos longitude 2 times sine square delta longitude difference. I think this should be lat 2. Delta longitude difference by 2 and C is 2 times tan inverse. Right, tan inverse 2 times root. I think, or this is a. I think we have to really look at it. I'll have to work out on one example. I think they have already given this example also. So if they are taking this difference, probably by we can try this problem. But right now I'm not sure. I haven't used it. Uh, but looks like this is a kind of a largest sphere that can be fitted between the two locations that are being given. So probably you can very well try this, but definitely I'm not sure whether sorry, I'm definitely not sure whether the distance currently this particular psi pi SciPy is not supporting this distance, or possibly if it is there with some other form. So we will have to try if there is a function that is already available. All right. But yeah, that's a good idea. Probably it looks like exclusively for the lat-lon, this is typically being used. Okay. Yeah, thanks for pointing that out. Probably we can try it out by using that example, and then we can see what is that brings as a difference when I am using the traditional lat-lon mechanism. What should be the difference if I am using a Euclidean distance? I'm really not sure what could be the difference if I just use a Euclidean distance. But yeah, probably we can quickly we can work it out, right? But that is an extra distance measure, especially if you are working with lat-lon kind of a data. Then we talk about the Hamming distance, which is, as we have just now said, it is primarily looking at the similarity between the two strings of the same length. So actually speaking, this Hamming distance can very well be utilized for comparing the two textual data elements. So between the two strings of the same length, so if I am applying it to the two different strings of the same length, it is primarily looking at the position of those characters. The position of the characters where the similarities exist and where the differences exist. So if you are talking about two 9-letter words, Euclidean is a 1 9-letter word, Manhattan is 1 9-letter word. So I can very well think of looking at the Hamming distance between the two words because the lengths are equal. So you can very well say, okay, first letter is E and the first letter is M, so it does not match. The second letter is U, the last letter, the second letter is A, it does not match. So like that, you can very well say how many matches are not there. So probably you can see that the last two are just AN, AN. So there is a matching that is happening. Whereas the other spaces, the matching is not occurring. So there are 7 spaces where the matching is not occurring. So you will say that the Hamming distance is 7. Right? So if you are comparing two strings, if I find that the distance is large, then those strings are very, very much away from each other. And if the distance is just 1 or 2, it means only one character is different or 2 characters are different between the two words. So you can very well find out the Hamming distance between the two strings. So Hamming distance is something that you may not want to use that much, especially in natural language processing kind of problems. You may want to look at the Hamming distance. But whereas in all the other kind of problems, you may not want to look at the Hamming distance. Majorly for regular problems, we would typically be looking at either the Euclidean or the Manhattan distance. But there could be some specific problems like Latlon kind of distances where you might very well use, as our friend Paras has already identified and hinted us, probably we may have to evaluate it. But definitely, it looks like that particular algorithm is primarily meant for the Latlon-based distances itself. All right. So now let's look at working on our data. We'll look at the distances and then we will also move on towards doing the clustering. So for that, I am taking my data. So this is a new data set that we would be working on. So I am taking a data set called countries data. So I am using different, so the data is about 167 countries, one row corresponding to each country. Right, I'm just explaining the data set. The data set contains 167 different countries, one row for each country, and overall there are 10 columns. If you look at it, first one is the country name, the mortality, the child mortality per 1,000 months in each of the countries, the exports of the country, the healthcare related index of the country, the imports, the average per capita income of the per capita income of the country, the inflation in that particular country, the life expectancy of the people in that country, total fertility rate in that country, and the GDP per capita. So these are the various variables, and let's say based on these variables, I want to identify clusters of countries. Right? So basically, I may want to group these countries into some logical groups. So I am not looking at, so possibly it can happen that if I am looking at only the child mortality, then the grouping might be different. I look at only the exports, then the groupings might be different. So it might very well be the case that depending on what I am looking at, if I am taking only one variable at a time, probably the grouping of the countries could be very much different. So rather than considering only one variable at a time, we want to take all the variables at a time and we want to create the groups of countries. Right? So Afghanistan, which other countries have similar pattern as Afghanistan? Argentina, which country is the most closest to Argentina, or which other 4-5 countries are more similar to Argentina? So these are some of the important things that we are trying to address, and probably we may want to group them accordingly. So if you really look at, if I'm printing the data, this is what it is. At least in this table, I could see that countries like, I just printed the top 10 observations. We could clearly see that the countries like Austria and Australia, they have very, very low child mortality. Whereas on the other side, a backward country like Angola and Afghanistan, they are having a very high child mortality. Similarly, on the other side, if I look at the exports, probably Angola is having a very high amount of exports in the top 10 observations that we have, the first 10 observations that we have seen. But probably the same Angola, in child mortality also, it is very, very high. Whereas when it comes to Afghanistan, child mortality is high, but the exports are very, very low. Right? So we could see different patterns. Health-wise, probably the index-wise, it's very low. Angola is very low on the health index. Whereas Austria is again much leading in terms of the health index. I'm just talking about the first 10 observations. Then imports wise also we could see some differences. The incomes wise, Australia and Austria are again on the very high side, whereas Afghanistan is very much on the lower side. Inflation wise, Angola is having a very high inflation, whereas Austria ends up into a very low inflation, and so on. We could clearly see the fertility rate also. Probably the Austria is one of the lowest in that first 10 observations, whereas Angola and Afghanistan, they are very, very much on the higher side. And similarly, GDP per capita also, we could see Australia and Austria on the higher side, whereas Afghanistan is very much on the lower side. So what we want our model to tell is group the various countries, create clusters of various countries, and tell me which countries are closer to each other and which countries are far away from each other. So you can very well take up different such kind of exercises, right? So basically now instead of having this country as a column, I am moving it to an index. So we are setting the index wherein we are taking out the country as a column, and we will replace, instead of 0, Afghanistan will come, instead of 1, Albania will come, and so on. That is what is like we are setting the index. So now when you look at the names of the columns, you could clearly see now you don't have your country name as a column name, because country name will have moved as the index name. So our columns are nothing but child mortality, exports, and so on. Only 9 columns are there. Then I can really look at the info. Info is giving you how many missing values are there. Obviously, I don't see any missing values here. All of them either float or integer, which means both are numerical kind of, all are numerical kind of column. But if there are few categorical columns, then we may have to even convert those categorical columns into numerical columns by applying a dummy variable analysis on the top of them, which we are already aware of. So I can find out, so the basic descriptive statistics is something that we will always do. So if I really look at these columns, the mean child mortality rate is 38 if I look at all the countries. The minimum is 2.6 for some country. Maximum is 208 for some country. So I could clearly see there is a great distinction between the various countries in terms of child mortality. Similarly, exports on an average is 41, but we have some countries which do not export at all, 0.1, and whereas on the other side, highly export oriented countries with a value of 200. Same way, health mean is 6.8, minimum is 1.8, and maximum is 17. So looks like all of them are very much skewed. Right? Imports wise, mean is 46, whereas the minimum is 0.06 and the maximum is 174. Similar. Now you could see almost all the variables. There could be a very high level of skewness. You can do a detailed descriptive statistics as we have done in our earlier module. So you can take up the code from the stat tools where you can get the detailed descriptive statistics as well. But this is very much sufficient. We are seeing that there is a very high skewed kind of a data. Inflation also on an average it is 7.78%. But we are seeing that there are countries with minus negative inflation, and at the same time we have few countries with a very high positive hyperinflationary kind of an environment. The life expectancy also on a similar ground, so 70, but varying between 30 to, oh, some countries are pretty poor with respect to life expectancy, whereas some countries are decent enough with 82.8. Fertility also, we could see that the minimum is 1.15, but it has gone even to 7.5 in some countries. So what we are observing is almost all the countries, they have a wide variety of variance, right? So which means it would always be better. Now in this case, we are talking about the distance. Right now, the problem comes when we are talking about the distance is, if I look at, let's say, fertility, hardly the values are between 1 to 8 or something, 1 to 7.5 or 1 to 8, right? So even if I talk about a country with a fertility of 2 and a country with a fertility of 7, the Euclidean distance between the two would be just around square root of 25, right? But I know that these two difference is a very, very big difference. Whereas on the other side, let's say you talk about income, right? We have values ranging from 19,200 to 1,25,000. So probably 20,000 for one and 19,200 for the other. This itself will account to square root of 800,000, 800 square, right? Which could be square root of 6,40,000. Obviously, the difference is a very, very minute difference. We all can understand it. This difference may not be a significant difference at all, right? Because the amount is varying between this. And so these two can be treated as very close by kind of differences. But whereas here, these two are like two extreme ends. So what we generally say is, if the size of the features is different, the size of the features is different, it is very much possible that the distances are influenced. If the size is different, then the distances are very much influenced by that particular feature which has a much bigger range compared to the features which have a very smaller range. So keeping that in perspective, for all distance kind of algorithms, we always say scaling is a very, very essential feature to be performed. So before you do any kind of distance-based algorithm, better execute the scaling, because scaling will bring some kind of normalization into the columns or into the features, and because of that this kind of heavy influence will not typically come up, right? So keeping that in mind, okay, we can look at how many unique values are there, and if there are any null values, we have already looked at that part. And if there are any missing values, better drop them, because we have to use all the variables or all the features to arrive at the best subgroup. So even if there is one missing value for a particular feature, better drop that row altogether, to drop that observation altogether. All right. Now, as we have said earlier, in case there are categorical variables in the data, better segregate them. What are we doing when we are doing a segregation? Just take the categorical column separately and numerical column separately, because we will apply the dummy variable transform. We will apply the dummy variable transform on the categorical variable. We will take the dummy variable transform on the categorical variables. And because of that dummy variable transform, even that would get transformed into a zeros or one, which will make it a numerical variable. But here we don't have dummy categorical variables. So even after doing the dummy variable transform, my data is going to remain the same, right? And after that, we are going to perform a standard scaling. Here we will not do any kind of non-linear transform on the data, right? We can very well do that as well, right? You can very well do a kind of box Cox or EO Johnson kind of a transform. So we can even try doing that as well, right? We will, but yeah, right now I haven't done it, so I just marked it. But if I have to do it again, I have to rerun right from the beginning, because obviously the values would have become overwritten. So either you can do a box Cox or a Yo Johnson transform to bring in the normality into the data. Right? In that case, what we say is we do not operate with respect to income, we will operate with respect to log income, or we will operate with respect to some other variable raised to the power of 0.4. Doesn't matter, because at the end of the day, we are trying to see which observations are closer enough. So probably if more observations are closer to normal, that can still bring in much more advantage to us. Okay, we'll start again. Otherwise, I'll run these, because that might give a better solution. Right? Probably I'll start from the scratch. Anyhow, we did not go too far off. Looks like I have to restart the runtime. So which means, anyhow, we can start from here. We'll just import the required libraries. And all these are simple calculations, which are, then we'll actually import our data. connecting to the Google Drive. We are taking the countries. Length is 167. Shape is 16710. We have got the head. We have taken the index. Then we have done this info, describe, right? We may not require the unique here. Just to remove any kind of, the unique is primarily done to remove any kind of zero variance kind of columns because they may not add much value to us. Also to identify if there are any blank column, blank rows, any missing values in any of the rows, so that the same can be eliminated. And if there are any missing values, probably you are dropping them. Then we are doing a kind of we are taking the categorical columns and the numerical columns separately. If there are any categorical columns, convert them into numerical columns by using your dummy variable analysis. So then I am taking the names of those columns. Here we are doing pre-processing. There are two major pre-processings that we are doing. One, we can do a box Cox or a EO Johnson. Instead of box Cox, I am using EO Johnson because when we have done this descriptive statistics, somewhere I have seen that some values are negative values. Right? Inflation is actually taking a negative value. So that is the reason I cannot directly apply box Cox on the data. I am applying a EO Johnson transformation on the data. Right? We can very well apply the EO Johnson transformation both, and after that we can even perform the scaling. Okay, I did not import the power transformer. So I'll say from sklearn dot reprocessing import power transformer. Then I can apply it. Okay, I don't have the training data here. So I'll update the X itself. I don't need this line altogether. Okay, so let me try now. Oh, sorry. Okay, so we have performed the box Cox transform as the EO Johnson transformation, and after that we have taken up the standard scaling also of the various observations. And based on that, we can very well look at the top 10 observations. So we can very well talk about the various observations, the top 10 observations. But yeah, their namings have typically gone off here. So that's where I can very well assign them the same indexes. So you could see now The call names are coming out well. Just one sec. Let us just observe what is happening. So X is a data frame containing 167 rows and 9 columns. Let's debug that. Then I have split them into categorical columns and numerical columns. Got the dummy variable creation. Still it is a data frame itself. Right? Once we created a data dummy variables also, it created a data frame. The column names is what we are considering as the columns of X. So the column names for us, this is our column name. So there are 9 different values for this. Then we are initially performing, let's say, let me do up to here first. Here I am performing a box Cox or a Yo-Johnson transformation. Once I perform the Yo-Johnson transform, X is still a kind of a data frame, right? Even after the Yo-Johnson transform, X is still a kind of a data frame only. Let me just print X. So after the box Cox transform also, X is still a data frame. But now what we are saying is we do the scaling, right? We will do the scaling where we are taking scaled X, right? So when I am doing the scaled X, let us see what is the scaled X now. Scaled X is also a data frame. Scaled underscore X is also a data frame. Now, what we are simply saying, okay, column names we are matching, right? Scaled X we have taken the column name, but the row names is what we have to match. So we can take the scaled X dot index. We can very well take that index to be the same as, I think we should have saved this index here. Right? It would have been better if we had saved this as the index. Okay, let's do that. So we'll call countries, country names is equal to, we'll call X dot index. Okay, so we get country names. Country names is a kind of an index with 167 value. So what we will do, we'll do this exercise. We will do the Box-Cox transfer, Johnson transformation, as well as the scaling of the data. We'll do both of them. And once we have done, we can do the scaling. But here it's only like the observations are numbered as 0, 1, 2, 3 kind, right? So better you give them the index. Instead of column names, you can give country names. Country names could be the name of the index. Right. So now if you are trying to print, you will get the country names also. So you could see that these are the variables, these are the values that are associated for each of the country. Now here there are two different arguments with respect to doing a Box-Cox transform or a Johnson transform on the data. So one, you actually work it out only in the raw form without doing a Box-Cox or a Johnson transform. Just do the scaling and go ahead. Because the data wise, even if the data is very extreme outliers kind of the data, obviously it has to be different from the rest of them. But on the other side, there is a different argument that comes in, where you can even do the non-linear transform on the data, because the variable itself, don't look at the variable as income, look at the variable as some logarithm of the income. So when I am looking at logarithm of the income as a variable rather than the income, obviously the distance between the observations would differ. So there are both ways, because the same variable by applying some transformation can become some other variable. Now, so take that variable because you know how to establish. Now it all depends, right? Income, if I take it as a logarithm of income, then probably the distance between the observations would be entirely different altogether. So this is a kind of a problem again, which is unresolved kind, right? Whether I should do a nonlinear transform also before applying the distances, or I should not. Because at the end of the day, the problem is very simple. At the end of the day, which mechanism is giving me the best differentiation across the clusters? Which mechanism is giving me a best differentiation across the clusters while increasing the cohesion among the observations in the cluster, right? So with this as the pre-processing, we are ready to apply our algorithm. So the first of those algorithms is the k-means algorithm. So we will initially discuss what is happening in the k-means algorithm in the background, and then we will do the computational part. So the first thing we will have to measure is pairwise distances. So I have 167 countries, right? So obviously what is going to happen is 167 by 167 pairwise distances are typically computed. So if I am talking about Afghanistan, right? What is the distance between Afghanistan and Albania? What is the distance between Afghanistan and Australia? What is the distance between Afghanistan and Austria? What is the distance between Afghanistan and Angola, Afghanistan and India, Afghanistan and Pakistan, Afghanistan and USA? Like that, Afghanistan versus the remaining 166 countries. Similarly, India versus the remaining 166 countries. Like that, pair-wise distances are typically computed. So that pairwise distances can very well be computed using this pairwise as a function. Now, even this pairwise as a function has, pairwise as a module has a function called pairwise distances. Now, this pairwise distances, this is a good function. You can here also that Haversine function I have not seen, right? Probably, I think that could be a newer edition, or it would be there only in a few packages, right? One is the Euclidean distance, or you can go with a city block, which is your Manhattan distance. There is a cosine similarity where the dot product between the vectors and the cosine of the angle cos theta between the two vectors is typically being considered for finding out the distance. That is what is called as a cosine similarity. Then you have Euclidean matrix, Euclidean distance. L1 and L2 are the regularizations that we discussed earlier when we discussed about penalization, and a Manhattan distance. So these are the only supported kind of metrics. But at the same time, you can also look at these are the other things that are supported. All these metrics also, the Canberra distance, Chebyshev distance, correlation-based distance, Hamming distance, Mahalanobis, all these are supported, but still you don't have your Haversine a distance mechanism. But here, you know that these are the various metrics that are supported, and based on that, you can get your numbers. So let us see. Pairwise distances are typically computed, wherein you could see here Afghanistan versus Afghanistan. Obviously, the distance is 0. But Afghanistan and Albania, the distance is 4.37 units. Afghanistan and Algeria, it is 4.21 units. Probably slightly closer to Angola. And in all the other cases, I could see that the distances are, probably from the ones that are presented, we are seeing that Angola is the smallest for Afghanistan. Whereas when I look at Albania, I could see that Algeria is slightly closer, or even Antigua and Barbuda is even more closer, or Armenia. For Albania, Armenia is much, much closer. Among the ones that are simply displayed out here, right? Uruguay is also decently close, but looks like Armenia is the closest. Right? Of course, so many are hidden, but out of the ones that are typically shown, I'm just saying. Probably for a country like Venezuela, even I'm seeing Algeria is good with Venezuela. Probably Venezuela is even more closer to Argentina in terms of all those various variables. Looks like Venezuela is more closer to Argentina than any other country which is being shown out here. So that is how what we will see is what is the kind of a distance that is existing between each of these countries. That is the first thing that we can think of. Now, based on that, we will look at this k-means clustering. Okay, so we will talk about the k-means clustering. What the k-means clustering typically does is, initially, you will have to specify the value for k. So probably, let's say you will specify 3. I'll tell you how we do that. But right now, let's say you want to specify k equal to 3. Now, the next aspect that you are going to do here is randomly out of these 167 observations that are there, randomly 3 observations are selected. Let's say the observation number 20, observation number 54, observation number 122. I don't know, it's just a random pick. Right? Observation 20, 54 and 122 are taken. Now, what will happen is all the observations from 1 to 167, right? 1 to 167, all the observations will be taken. Now, the distance between 1 and 20, 1 and 54, 1 and 122, because these three are taken as initial cluster centers. Initial cluster centers. That's a random allotment. Right? Well, I'll tell you how we handle this randomness, but that's a random allotment. So we will take the initial cluster centers, these three. Then each of these 167 observations, we will try to find out the distances with each of these three. So the distance between first one and the 20th one, let's say it is 2 units. First one and the 54th one, let's say it is 3 units. First one and the 122nd one, let's say it is 1.5 units. So what we say is, this first one is closest to 122nd one. So push this, the first observation into this cluster. So similarly, next you start with the second observation, the same. So whichever of these three is closest to the second observation, you put the second observation into that cluster. Let's say this goes here. The third observation goes here. The fourth is also here. Similarly, like this, what could happen is, let's say 150th observation is here, 167th observation is here. Like that, we get some kind of allotment. Now what we will do is, all the observations that came into this particular group, right? All the observations that came into this particular group, there will be an average of all the values. There will be a column-wise average for each column for the entire observations that are there in this group. Similarly, there will be a column-wise averaging that happens for all the elements in this group. There will be a column-wise averaging that will happen for the elements in this group. Now, based on this, what is happening? I get a it's a new observation that I'm going to get now, because it's the average of all these observations. So this would be like a x dash, x1 dash kind of an observation. So this would be like an x2 dash kind of an observation, x3 dash kind of an observation. Now again, the same process continues. Now again, individually, I can take 1 to 167. I will find out the distance between 1 and 160, 1 and x1 dash, 1 and x2 dash, 1 and x3 dash. So again, we are seeing which one is one a part of, is one closest to x1 dash or x2 dash or x3 dash. So again, whichever is the one that is closest to, you put this one into that cluster. So like this, the process keeps on repeating until there is no change in the composition of the cluster. As long as the same cluster, I mean the observations are not shuffling between the clusters. As long as the observations are not shuffling between the clusters, until the observations are shuffling between the clusters, you will still continue this process, right? Otherwise, if the shuffling is stabilized and no further shuffling is happening across the clusters, then you will stop this entire exercise. Then you will stop this entire exercise, and that is what we call as the composition of each of the clusters. So what could very well happen is we can start with one cluster. Obviously, there is no cluster. If we say one cluster, it means that all the 167 observations into one cluster, one group. In that case, that is what we typically call as your base or a null cluster, right? And we can find out what is the kind of sum of squared errors. We'll talk about them, the metrics. Sum of squared errors for one cluster solution, for two cluster solution, and so on. And based on that, we can talk about which solution is much better. How many clusters are an ideal number? We can very well get into that kind of a mechanism. So let's look at it. Unless there are some specific questions, we will look at some of the notes that is available, and then we will jump on into the calculation. So K-means allows us to define the required number of clusters. I have to very well define how many clusters. So probably sometimes people call that as a drawback as well, because the system does not automatically determine how many clusters are required. You have to explicitly give that information as the input in terms of how many clusters do you require to build. Now, we will first start by taking an arbitrary number. As I told you, I can start with 3 as the number of clusters. So that is an arbitrary number, right? Now, there are two different ways of defining what is the best value of K. But to start with, we will have to start with a random cluster, a random number for the number of clusters. So the moment we say we have taken 3 clusters, then our K-means algorithm will choose 3 random points as the centroid. As we have already taken in our example, the 3 random points are taken as the centroid. Then it will find out the distances. Primarily, it finds out the Euclidean distances only between each observation, each of the 167 observations, and each of the 3 centroids that we had. Centroids are also the observations that are picked up randomly based on the number of clusters that we have indicated. The algorithm, after measuring the distances of all the data points from the centroid, associates each data point with a centroid based on its proximity. It will push each observation into a different cluster depending on which one is closest to it and which ones are the farthest. So generally the closest one is where that particular observation will be pushed towards. So which means wherever the distance is the lowest, that would be the cluster to which each observation will be put. To measure how good the 3 clusters are separated, we use Silhouette score. Okay, so here we are talking about something called, I don't know how to spell it. I generally spell it as Silhouette score. So here we will talk in terms of the distance between the clusters and distance within the cluster. So it's a kind of a measure. Probably if I'm talking about this as the distance between the clusters is B and within the clusters is A, generally it is taken as A minus B divided by the maximum of A comma B. So this is what is a typical measure that is used for Silhouette score, right? So obviously you could see within the clusters, the distance should be very, very small. And between the clusters, the distance should be very large. So sometimes people also, right? B is the distance between the clusters, which should be very large, distance should be very, very close. So which means when I take B minus A, obviously this number would be much, much larger. So where my B minus A is very, very high, that combination is what we would typically say that that would be the ideal number of clusters. So that is where we are coming out to. So we are saying to measure how good the three clusters are separated. So the separation, now whatever is the distance that you are using, whatever is the transformation that you are doing hardly matters, right? Because at the end of the day, I will use this measure to see which model or which how many cluster solution is a better solution to the data out here. I can very well use that kind of a solution directly. So it hardly matters to me whether I should use Manhattan distance or Euclidean distance, because at the end of the day, I will look at the Silhouette score, which talks about the distinction between the within the clusters and between the clusters. So sometimes we can also use the elbow method, right? Elbow method, but somewhere it is not. I mean, there is a subjectivity element, especially when you are going with the elbow method. There is definitely an element of subjectivity in terms of which method is the best method, or which what is the number of K? What is the number for K? Which is the number of clusters. So we are actually varying the number of clusters from 1 to square root of n generally. So because I have 167 observations altogether, probably I may go up to 13, because 167, 169 is square root of 13. So I may go to either 12 or 13. Now for each value of K, we will calculate weighted cluster sum of square. This is another measure. Weighted cluster sum of square. So if I'm talking about, let's say all these observations, they are, so are probably we can say the observations 1, 2, 7, 12, 25. Let's say these 5 observations are put into one cluster called C1. Now, the values of all these 5 are averaged, and that value is called as the cluster center for C1. Right? For each column, For each column, the values of all these 5 rows are averaged. So based on that, we will get a cluster center. What is expected is you find out the distance of each of these observations to the cluster center. You add up all those distances, and that is called as the weighted clustered sum of squares. Right? Weighted clustered sum of squares. Obviously, now if you see, if the number of clusters is equal to number of observations, right? Then you will find that the weighted cluster sum of squares will always become 0, because there is only one observation in each cluster. So the center of the cluster and the observation themselves both are one and the same. There is no difference between the center of the cluster and the observation. So obviously you may get the weighted cluster sum of squares to be 0. You may very well say that this cluster classification is really good. But what is the point? I'll get 167 clusters, which is as good as my data itself. No grouping, nothing. So which means getting a WCSS, which is a weighted cluster sum of squares to 0, is not an ideal solution. Similarly, on the other side, if only one cluster is there, obviously my weighted cluster sum of squares is going to be much, much higher. So lower the number of clusters, only one cluster, lower value of k means my weighted cluster sum of squares is going to be very high. Whereas if I go with a higher value of k, probably my weighted cluster sum of squares is going to be 0. Now, but this is no problem, no use, because my total number of clusters is exactly becoming equal to the total number of observations. Clustering has to make my life easy by creating 4 or 5 groups or max of 10 groups, but out of the whole data, but not one country into one group. So which means there is a trade-off. So what we do in case of a trade-off is we will try to see that basically the kind of fall that is happening in the weighted cluster sum of squares, suddenly after some time the fall will actually flatten out. The fall will not be much higher. So the other way of saying is the fall percentage, right? The fall percentage after a certain point, it will flatten out. And probably after that, it might again grow, but here it has flattened out. So which means the fall is almost negligible. So the best way to talk about is, we'll see from the data. So the fall can become negligible and so almost flatten out. So this flattening out is a kind of scenario. This flattening out is a kind of a scenario that probably that is the maximum number of clusters that you can think of. That is the maximum number of clusters that you can think of. Okay. So the elbow method can really handle that kind of a solution. We are actually varying the number of clusters from 1 to the square root of number of observations. For each value of k, you can calculate the weighted cluster sum of squares. The within the cluster sum of square. So within the observations that are a part of the cluster, here we will not compute the between cluster sum of square. We only look at within cluster sum of squares. Sum of the squared distance between each point and centroid in the cluster. We have talked about this concept already. right? WCSS value is largest when k equal to 1 because all of them are being put into one cluster. So one single cluster center, so weighted, the within the cluster sum of squares is going to be the largest. And as I told you, when k is equal to the total number of observations, then your WCSS will be the lowest or it can be equal to 0 as such. Then I talked about the out score also. Clusters are well apart from each other as the Silhouette score is closer to 1, as I have already talked about. The between the clusters, the distance is very high. Within the cluster, the distance is very low. In that case, my B minus A is going to be very, very close to B. And divided by max of A and B will always be B. So the ratio could be very much close to 1. So when the score is coming very, very close to 1, then we can say that the clusters are well apart from each other and they can be very clearly distinguishable. Whereas if the score, Silhouette score is somewhere around 0, then B and A are more or less equal. So between the cluster sum of the squares and within the cluster sum of squares are more or less equal. So which means the distances is not significant and the clusters are not doing any great job. And if you are getting the other way, the score is coming to -1, probably your B is very, very small, but A is very, very high. So which means the between clusters, there is not much of a difference. But within the clusters, there is a huge difference. So which means the clusters are very wrongly assigned. Right? So the Silhouette score is a better way to compare the various solutions that are coming out because of different values of k. So if we really look at now what I am doing, I'll first do a one cluster solution. So I'm saying only one cluster. K means I'll fit one cluster solution and I'll look at the weight of the within cluster sum of squares. Within cluster sum of squares is otherwise called as inertia. Within cluster sum of squares is otherwise called as inertia. So let us see the solution. So it is saying that all of the observations are allotted to a cluster 0 and the within cluster sum of squares is around 1503. That is the within cluster sum of squares that is coming up. It has come out to 1503. So now my job is to continue with 2 cluster, 3 cluster, 4 cluster and see that to what extent the within cluster sum of squares is coming down. To a large extent, what we will see is that if I am increasing the number of clusters, the within cluster sum of squares is always going to fall. But how big it is falling is what is the most important thing. So the same problem, if I am solving with 2 clusters rather than 1 cluster, I can solve with 2 clusters. I'm seeing that the within cluster sum of squares has come down to 903. So from 1500, there has been a fall to 900. Right? From 1500, there has been a fall to 900. Now the same exercise, let's say if I continue with 3 clusters, right? If I see this with 3 clusters, okay, it has fallen down to 758. From 903, there is a fall to 758. So we can see what is the kind of a fall. Probably if I'm going with a 4 cluster solution, let's say it has come to 668. So there is a fall that is coming every time, but how big is that fall? Now this is what we are going to observe the next, but we are just moving forward. Let's say I have created 4 clusters. I can store those cluster names to my data. Based on that, I can look at, okay, my X is, okay, fair enough. So I can very well say that what we will do is again to this X, we'll give our index names. X dot okay. So we can see that each of them, now you see the Afghanistan and Angola, both of them are a part of the cluster 0. Albania and Algeria are a part of cluster 2. Antigua and Barbuda are a part of cluster 3. Probably the last few countries also we can see. You see, Vanuatu and Yemen and Zambia, they are all clubbed with Afghanistan and Angola. Venezuela and Vietnam are clubbed with Albania and Algeria. So in a 4 cluster solution that we have created, we know which country is going as a part of which cluster. Now we can very well analyze on, or probably if I go with the 2 cluster itself, we'll first go with the 2 cluster only, understand all these, and then we'll come back to 3 and 4 cluster solution. Right. So now you could see that Afghanistan and Angola are a part of one cluster called cluster 1. The remaining 3 countries are a part of cluster 0. Similarly, in case of tail also, Venezuela and Vietnam are a part of this cluster, whereas Vanuatu, Yemen and Zambia are a part of cluster 1. So we can very well look at the centroids of each of the clusters. What does each of these cluster mean? What does cluster 0 mean? And what does cluster 1 mean? We could clearly see here that for cluster 0, the child mortality is negative, whereas for cluster 1 it is for, remember these are all scaled data, so you will always find negative and positives. So positive means very high, negative means very low. So you can very well say that the child mortality, the average child mortality is very high in the cluster 1. So cluster 1 contains Afghanistan, Angola, Vanuatu, etc. Very clear cut difference because the average is varying between minus 0.66 and plus 1.02. Exports wise, the cluster 0 is having a higher exports, whereas cluster 1 has lower exports. Health wise, again, cluster 1 is having a negative, which means a lower health index, whereas cluster 0 is having a higher positive health index. Imports wise, you don't see too big a difference, These two are just very close on either side of positive and negative. Not much of a difference compared to other. Child mortality is looking like a very big difference. Probably exports is also decently different, but imports, we are not seeing a kind of a big difference between the clusters. Whereas in case of income, we are seeing a big difference again, right? Cluster 1 contains very low income countries, whereas cluster 0 is the high income countries. And same way, inflation wise, cluster 1 is high inflation countries, whereas cluster 0 contains low inflation kind of countries on an average. Life expectancy in cluster 1 is very low, whereas it is high in cluster 0. Fertility is very low in cluster 0 and high in cluster 1, right? And probably you can also talk about the GDP per capita is higher in cluster 0 and lower in cluster 1. And of course, there has been a kind of a unnecessary addition. This cluster may not be required for us at all. So that is how we got the centroids. You can very well look at for each of them, you can take out the means and you can very well work it out. But yeah, this is much better if you can take it with respect to, so you can very well verify for each of them. You can verify the mean values, which is another way of getting this. Oh, this is cluster, right? So you could clearly see here the same calculation that we have done in this table. We can even get it in this mechanism as well. So now the next thing that we say is, okay, if I do this as a 3-cluster solution instead of a 2-cluster solution, are we clearly differentiating across the country? Now some countries are into cluster 0, some are into cluster 1, some are into cluster 2. All right. So we'll see what is happening there. You could clearly see here, cluster 0 contains very low child mortality. Right? If you look at out of the 3, this is the lowest. So your interpretation is cluster 0 contains very child mortality, high exports. You are defining the cluster like this: high exports, high healthcare index, high in terms of imports. So it's high both in exports and imports. High in terms of income, very low in terms of inflation, high in terms of life expectancy, low in terms of fertility, high in terms of GDP per capita. So that is what is the definition of cluster 0. That is how we are defining the cluster 0. So you could clearly see those are probably the kind of developed countries, right? Whereas when you look at cluster 1, very high in terms of child mortality, very low, lowest out of the 3 clusters in terms of exports, healthcare wise slightly moderate, again imports wise, slightly moderate. So because they are overlapping with the others. Income wise, very low. Inflation wise, on the higher side. Life expectancy is very low. So some of the variables are very clearly separable. Some of the variables are not that clearly separable. Fertility is very high, GDP is very low. So whereas when it comes to the cluster 2, there is no significant variable where they are very high or very low compared to others. For almost all of them, they are somewhere in the middle. Not a clear, unless you say they are health wise, their health care index is the lowest. That is one variable that I can talk of, but almost in all the other variables, they are somewhere in the middle. Probably their inflation is much higher, but in all the other variables, they are somewhere in the middle. So when you don't get a better definition for a particular cluster, then it means that that kind of a cluster solution may not be a useful solution at all. So that's one simple way that you can make out what kind of a cluster solution is better for us. All right. So you can very well talk about the total within the cluster kind of a distance. So now that I have created 3 clusters, it is telling me that my cluster 0 contains 50 countries and only 222 is the within cluster distance. So cluster 0 is seeing tight packing because within cluster distance is the lesser. Whereas you look at cluster 1, that is also packed. 60 members are there and 286 is the within cluster distance. But look at the cluster 2, only 57 members are there, lesser compared to cluster 1, but their cluster distance is very high. Now, this is where some thought comes up in terms of whether we require the second, cluster 2, or only a 2 cluster solution is more appropriate. Okay, so I think we'll stop this here. We have a few more discussions that we need to do with respect to the k-means clustering. Probably in our next session, we will complete off that discussion, and after that, we would move on to the other 2 methods of clustering as well. Meanwhile, if there are any queries, we can discuss them. Otherwise, I think we can end this session